Welcome to this explainer. Okay, today we're diving deep into the fundamental mechanics of the quantum world. As someone who follows science, you already know the big buzzwords: superposition, tunneling, entanglement. But today we're really going to connect the dots on exactly how these microscopic rules dictate our reality. We're breaking down the mechanics of the universe, and we're going to make it simple.
Okay, let's dive into this. Here is our roadmap. 1. Classical versus quantum reality. 2. The birth of quantum physics. 3. Defying everyday macro logic. 4. Pop culture and multiverses. And 5. Real-world quantum applications.
Section 1. Classical versus quantum reality. Breaking the rules of the world we know.
You know, our human brains are incredible, but they're entirely hardwired for the macroscopic world. In our familiar classical reality, things are pretty straightforward. A car is either at rest or it's moving. A system is completely on or it's off, right? There's no middle ground. But down on the fundamental scale of the most basic particles we're made of, these rigid binaries just completely fall apart. Because a microscopic particle's wave function hasn't collapsed into a single definitive state yet, it actually exists in a number of states all at once.
And this brilliantly illustrates one of the most famous analogies in all of science: Schrödinger's cat. In the fundamental quantum realm, the cat wouldn't be just dead or just alive. Because the system hasn't been observed and forced to pick a state, it exists as a probability distribution, literally both dead and alive at the exact same time. This mechanical reality is what we call superposition, where a particle exists in a combination of states simultaneously.
Let's actually ground our vocabulary on how this works. The word quantum is simply Latin for how much. In physics, it means that energy isn't some continuous flowing stream. Instead, it's quantized into discrete absolute minimum amounts. Think of it like walking upstairs instead of a smooth ramp. We're dealing with the foundational building blocks of our world, the most elementary particles like electrons, protons, quarks, and photons, and the specific, indivisible packets of energy they trade.
Section 2. The birth of quantum physics, when classical physics wasn't enough.
Let's move to and see how this builds. Because regular classical physics, dealing with Newton's laws of motion, was great for orbital mechanics and macro engineering. But eventually, scientists stumbled onto a historical mystery where those reliable laws completely failed. Back in the early 1900s, the photoelectric effect baffled everyone. See, when light hits metal, it knocks off electrons. Classical physics said, hey, if you just crank up the brightness of the light, more electrons should escape. But reality didn't agree. It was actually the color, the frequency of the light, that determined if electrons were emitted. Then Max Planck proposed that light waves carry energy in specific, discrete packets called quanta. Building directly on that, Albert Einstein showed that light acts as both a continuous wave and a discrete particle, which was later named the photon. Basically, classical physics was broken and quantum mechanics was born.
Section 3. Defying everyday macro logic. Why our brains struggle with the microscopic.
As we get into some of the stranger mechanics, it's worth noting that our brains evolved to understand friction and gravity, not the absolute weirdness of microscopic probabilities. Think about this for a second. How do you cross a massive alligator-infested wall without enough energy to climb it or dig under it? In our macroscopic world, if you face a massive physical barrier and lack the energy to overcome it, well, you're simply stuck. You aren't getting to the other side.
But in the microscopic world, you just go straight through. Welcome to quantum tunneling. Unlike facing a literal brick wall, a quantum particle doesn't have a fixed, precise location. Its position is actually a probability wave. When that wave hits an energy barrier, a tiny fraction of that probability wave extends into and past the barrier. Because that probability exists on the other side, the particle can simply tunnel right through, even without the requisite energy.
So the crucial point is, this isn't just theory. This bizarre mechanical loophole is directly responsible for the nuclear fusion that fuels the energy production of stars. Without particles defying macro logic and tunneling through seemingly impossible repulsive energy barriers, the stars in our night sky, including our very own sun, simply wouldn't be able to fuse hydrogen. They literally wouldn't shine.
Section 4. Pop culture and multiverses, from sci-fi to real physics.
Now, as complicated as these mechanics are, popular culture absolutely loves them. Marvel movies, for instance, dramatize these very microscopic phenomena, blowing them up onto a massive theatrical scale. In quantum mechanics, a physicist won't say an electron is definitively at point A. Instead, they operate on probabilities, stating the electron is most likely to exist in this range of lengths.
Mathematically, that exact same probability distribution can be interpreted as the electron existing simultaneously in different realities across that possible range.
Trace the math and you see the movie magic. Step 1, the underlying math predicts a particle exists in a probable range of positions. Step 2, this implies the particle is actually existing in different positions across different realities all at once. And step 3, Hollywood takes this microscopic concept and massively magnifies it into separate, fully formed multiple universes. It's a direct bridge from real-world probability mechanics to your favorite blockbusters.
And of course, we literally can't talk about pop culture physics without time travel. Time travel presents a massive logical problem known as the grandfather paradox. It basically states that if you change the past, the future changes. If you travel back in time to kill a villain, you prevent the very apocalypse that caused you to time travel in the first place. But wait, if it never happens, you never go back, and you never stop them. It's a complete breakdown of classical logic.
Now, what's really interesting about this is how Avengers Endgame actually used real theoretical physics to solve this. While the grandfather paradox completely breaks classical logic because you cannot logically change the past, David Deutsch's quantum fix bypasses the problem by treating macro events just like quantum particles, as probabilities. This means that changing the past only has a probability of happening. You might go back, but probabilistically speaking, the wave function of that event might not allow you to actually alter the timeline.
The writers utilize this quantum loophole perfectly. By returning the infinity stones to their exact timelines, they avoid any changes due to the missing stones, keeping everything probabilistically stable. It's an incredibly clever cinematic fix, taking real-world probabilistic quantum mechanics and applying them flawlessly to a macro scale.
Section 5. Real-world quantum applications. The future of our daily lives.
As fun as multiverses and time travel are, quantum mechanics is absolutely not just movie magic. It is a rapidly expanding domain of modern, serious science that is heavily integrating into our reality right now. By mastering how the quantum world works, we're building quantum computers aimed at solving tasks exponentially faster than classical architecture ever could. We're creating better communication networks using quantum encryption for unprecedented system privacy. Energy production in nuclear reactors relies entirely on harnessing fission via these quantum rules. And in astrophysics, we're using this exact math to map the universe's most basic building blocks.
So, it leaves us with this. If the most fundamental building blocks of our universe, the very stuff you and I are made of, operate on probabilities and completely defy our everyday and macroscopic logic, what else about our reality are we completely misunderstanding? It's a massive, beautiful universe out there, and quantum physics shows us we've really only just scratched the surface. Thank you so much for joining me on this explainer. Keep asking questions and stay curious.